Mars has long captivated our imagination, but what if our quest to find life there has already altered its landscape? 50 years ago, NASA's Viking missions landed on the Red Planet, equipped with cutting-edge technology to search for life. Yet, in our eagerness, did we unintentionally destroy the very evidence we sought? From mysterious chemical reactions to the potential contamination of Martian soil, the story of Mars is filled with unexpected twists. As we piece together the clues, the truth about our impact on Mars might be more surprising than we ever anticipated. Stay tuned as we unravel this cosmic mystery. 50 years ago, NASA's Viking missions landed on the Red Planet, equipped with cutting-edge technology to search for life. Yet, in our eagerness, did we unintentionally destroy the very evidence we sought? From mysterious chemical reactions to the potential contamination of Martian soil, the story of Mars is filled with unexpected twists. As we piece together the clues, the truth about our impact on Mars might be more surprising than we ever anticipated. Stay tuned as we unravel this cosmic mystery. The Viking Landers, launched by NASA in 1975, were the first U.S. missions to land on Mars and conduct experiments directly on the Martian surface. Their primary objective was to search for signs of life. The landers carried a suite of scientific instruments designed to analyze Martian soil and atmosphere, including experiments to detect metabolic processes indicative of living organisms. One of the most significant aspects of the Viking missions was their life detection experiments. These included the labeled release LR experiment, which mixed Martian soil with a nutrient solution containing radioactive carbon. The idea was that if microorganisms were present, they would metabolize the nutrients and release radioactive gas, which could be detected. Surprisingly, the LR experiment yielded positive results, suggesting metabolic activity. However, the lack of organic molecules detected by the Gas Chromatograph-Mass Spectrometer, GCMS, led scientists to conclude that the results were due to non-biological chemical reactions. The Viking missions also highlighted the challenges of planetary protection and contamination. Despite rigorous sterilization procedures, there was concern that Earth microbes might have inadvertently been transported to Mars, potentially contaminating the Martian environment. This raised ethical and scientific questions about the integrity of life detection experiments and the possibility of harming potential Martian ecosystems. Furthermore, the Viking Landers' findings have been re-evaluated in light of new discoveries, such as the presence of perchlorates in Martian soil, which could have affected the experiment's outcomes. These insights have sparked ongoing debates about the interpretation of Viking data and the possibility that life on Mars might have been overlooked or even destroyed by the landers' activities. Contamination protocols are critical in space exploration, particularly when searching for life on other planets like Mars. These protocols are designed to prevent the forward contamination of celestial bodies with Earth-originating organisms, which could compromise scientific investigations and potentially harm extraterrestrial ecosystems. During the Viking missions, NASA implemented stringent sterilization procedures to minimize the risk of contaminating Mars. The spacecraft were subjected to dry heat microbial reduction, a process that involved baking the landers at high temperatures to kill any microorganisms. This was in accordance with the planetary protection policies established by the Committee on Space Research, or COSPAR, which aimed to preserve the natural state of celestial bodies. Despite these efforts, the effectiveness of sterilization techniques has been a topic of debate. Some scientists argue that certain extremophiles, organisms capable of surviving in extreme conditions, might withstand the sterilization process. This raises concerns about the potential for Earth microbes to survive the journey to Mars and establish themselves in the Martian environment, thereby confounding the search for indigenous Martian life. The Viking missions also highlighted the challenges of implementing contamination protocols in practice. The complexity of spacecraft design and the harsh conditions of space travel make it difficult to ensure complete sterilization. Additionally, the detection of perchlorates in Martian soil, which can interfere with life detection experiments, underscores the need for robust contamination control to avoid false positives or negatives. In recent years, advancements in sterilization technology and a better understanding of microbial resilience have informed the development of more effective contamination protocols. These improvements are crucial for future missions, as they aim to explore potentially habitable environments on Mars and other celestial bodies. Sterilization techniques are a cornerstone of planetary protection efforts. particularly in missions aimed at exploring potentially habitable environments on other planets, such as Mars. These techniques are designed to eliminate Earth-originating microorganisms from spacecraft to prevent forward contamination, which could compromise scientific investigations and potentially harm extraterrestrial ecosystems. During the Viking missions, NASA employed dry heat microbial reduction as the primary sterilization method. This process involved heating the spacecraft to high temperatures for extended periods to kill any microorganisms. The goal was to reduce the microbial load to a level that would minimize the risk of contaminating the Martian environment. This method was chosen because it was effective against a wide range of microbial life and could be applied to the entire spacecraft. However, the effectiveness of sterilization techniques has been a subject of ongoing debate. Some extremophiles, which are organisms capable of surviving in extreme conditions, might withstand the sterilization process. These resilient microbes could potentially survive the journey to Mars and establish themselves in the Martian environment, complicating the search for indigenous Martian life. The Viking missions underscored the challenges of implementing sterilization techniques in practice. The complexity of spacecraft design, with numerous nooks and crannies, makes it difficult to ensure complete sterilization. Additionally, the harsh conditions of space travel, such as radiation and vacuum, can affect the efficacy of sterilization methods. In response to these challenges, NASA and other space agencies have continued to refine sterilization techniques. Advances in technology have led to the development of more effective methods such as vapor phase hydrogen peroxide and gamma irradiation, which offer broader microbial inactivation capabilities. Martian soil experiments conducted by the Viking Landers were pivotal in the quest to detect life on Mars. These experiments were designed to analyze the chemical and biological properties of Martian soil, providing insights into the planet's potential to support life. The Viking Landers carried three primary biology experiments: the labeled release, LR, the gas exchange, GEX, and the pyrolytic release, PR, experiments. Each was designed to detect metabolic processes that might indicate the presence of microorganisms. Labeled Release LR Experiment. This experiment mixed Martian soil with a nutrient solution containing radioactive carbon. The hypothesis was that if microorganisms were present, they would metabolize the nutrients and release radioactive gas, which could be detected. The LR experiment produced results that initially suggested metabolic activity, sparking excitement about the possibility of life. However, the lack of organic molecules detected by the Gas Chromatograph-Mass Spectrometer, GCMS, led to skepticism about these findings. Gas exchange, GEX, experiment. This experiment aimed to detect gases released or absorbed by Martian soil when exposed to a nutrient solution. The results showed changes in gas composition, but these were attributed to non-biological chemical reactions rather than biological activity. Pyrolytic release, PR, experiment. This experiment tested whether Martian soil could incorporate carbon from a simulated Martian atmosphere. The results were inconclusive, with no definitive evidence of biological activity. The Viking soil experiments highlighted the complexity of interpreting data from extraterrestrial environments. The presence of perchlorates in Martian soil, discovered decades later, may have affected the experiment's outcomes by breaking down organic molecules during heating, leading to false negatives. The detection of organic molecules on Mars has been a central focus of astrobiological research, as these molecules are fundamental building blocks of life. During the Viking missions in the 1970s, the search for organics was a key objective, but the results were initially disappointing and controversial. The Viking Landers were equipped with a Gas Chromatograph-Mass Spectrometer, GCMS, designed to analyze Martian soil for organic compounds. Surprisingly, the GCMS detected no organic molecules, leading scientists to conclude that Mars was devoid of the organic chemistry necessary for life. This finding was puzzling, especially given the positive results from the labeled release experiment, which suggested metabolic activity. Decades later, the discovery of perchlorates in Martian soil by the Phoenix lander in 2008 provided a possible explanation for the Viking results. Perchlorates are highly reactive chlorine-based compounds that can destroy organic molecules when heated. During the Viking experiments, the soil samples were heated to release gases for analysis, which may have caused any present organics to decompose, resulting in false negatives. This revelation prompted a re-evaluation of the Viking data and underscored the need for more sophisticated techniques to detect organics on Mars. Subsequent missions, such as the Mars Science Laboratory's Curiosity rover, have employed advanced instruments capable of detecting organics without the need for high-temperature processing. Curiosity has since detected simple organic molecules, such as chlorobenzene and dichloroethane in Martian rocks and soil, suggesting that organics are present on Mars, albeit in low concentrations. The discovery of perchlorates in Martian soil has significantly influenced our understanding of the planet's chemistry and the interpretation of past life detection experiments. Perchlorates are chlorine-based compounds that are highly reactive, especially when heated, and they have profound implications for both the potential habitability of Mars and the results of previous missions. Perchlorates were first detected on Mars by the Phoenix lander in 2008, and their presence was later confirmed by the Curiosity rover. These compounds are known to lower the freezing point of water, which could allow liquid brines to exist transiently on the Martian surface or subsurface, potentially providing a niche environment for life. However, their reactivity poses challenges for the detection of organic molecules, which are crucial for identifying potential biosignatures. During the Viking missions, the presence of perchlorates was unknown. The Viking labeled release experiment showed signs of metabolic activity, but the Gas Chromatograph-Mass Spectrometer, or GCMS, failed to detect organic molecules. It is now believed that perchlorates in the Martian soil may have decomposed any organics present during the high-temperature analysis, leading to false negatives. When heated, perchlorates can oxidize organic compounds, breaking them down into carbon dioxide and other gases, which would not be detected as organics by the GCMS. This understanding has prompted a re-evaluation of the Viking results and has influenced the design of subsequent missions. Modern instruments, like those on the Curiosity rover, are designed to detect organics without the need for high-temperature processing, thereby avoiding the destructive effects of perchlorates. The Viking mission's life detection experiments, particularly the labeled release experiment, produced results that have been the subject of debate for decades. The labeled release experiment showed signs of metabolic activity, which some interpreted as evidence of life. However, the lack of detected organic molecules led to skepticism, and the results were largely attributed to non-biological chemical reactions. This situation highlights the issue of false negative results in the search for life on Mars. False negatives occur when an experiment fails to detect a phenomenon that is actually present. In the context of the Viking missions, several factors could have contributed to false negatives in the detection of life or organic molecules. One major factor is the presence of perchlorates in Martian soil, which were unknown at the time of the Viking missions. Perchlorates can decompose organic molecules when heated, potentially destroying any evidence of organics during the Viking GCMS analysis. Additionally, the Viking instruments may not have been sensitive enough to detect low concentrations of organics or life forms that differ significantly from terrestrial life. The harsh Martian environment, with its high radiation levels and extreme temperatures, could also mean that any existing life is sparse or exists in forms that are not easily detectable with the technology available at the time. The interpretation of the Viking results has been further complicated by the discovery of recurring slope lineae, or RSL, and other features that suggest the presence of liquid water, albeit transiently, on Mars. These findings have renewed interest in the possibility of life and have led to calls for more advanced life detection experiments. Sample handling procedures are a critical component of planetary exploration missions, particularly those aimed at detecting signs of life. The way samples are collected, processed, and analyzed can significantly impact the results of scientific experiments, as seen in the Viking missions to Mars. During the Viking missions, the landers were equipped with robotic arms to collect soil samples from the Martian surface. These samples were then delivered to onboard instruments for analysis. The handling of these samples was crucial, as any contamination or alteration could affect the integrity of the data collected. One of the primary concerns in sample handling is the potential for contamination with Earth-originating materials. Despite rigorous sterilization procedures, there is always a risk that terrestrial microbes or organic compounds could be introduced during the collection and analysis process. This could lead to false positives in life detection experiments, where Earth life is mistaken for Martian life. Another challenge is the preservation of the sample's original state. The Martian environment is vastly different from Earth's, and exposure to the spacecraft's conditions could alter the sample's properties. For instance, changes in temperature, pressure, or humidity could affect the chemical composition of the soil, potentially leading to false negatives or misinterpretations of the data. The Viking missions also highlighted the importance of understanding the local Martian environment when designing sample handling procedures. The presence of reactive chemicals such as perchlorates was not known at the time, and their interaction with the samples during analysis may have affected the results. Future missions aim to improve sample handling by incorporating more advanced technologies and techniques. For example, the Mars 2020 Perseverance rover is equipped with a sophisticated sample caching system designed to collect and store samples for potential return to Earth. This approach allows for more detailed analysis using Earth-based laboratories where contamination can be more effectively controlled and a wider range of tests can be conducted. Instrument sensitivity is a crucial factor in the success of planetary exploration missions, particularly those aimed at detecting signs of life or organic compounds. The sensitivity of scientific instruments determines their ability to detect low concentrations of target molecules, which is essential when exploring environments like Mars, where potential biosignatures may be present in trace amounts. During the Viking missions, the Gas Chromatograph-Mass Spectrometer, or GCMS, was used to analyze Martian soil for organic molecules. However, it failed to detect any organics, leading to the conclusion that Mars was devoid of the organic chemistry necessary for life. This result was surprising, especially given the positive results from the labeled release experiment, which suggested metabolic activity. The discrepancy raised questions about the sensitivity of the GCMS and whether it was adequate for detecting the low levels of organics that might exist on Mars. Several factors can affect instrument sensitivity, including the detection limits of the technology, the presence of interfering substances, and the environmental conditions. For instance, the presence of perchlorates in Martian soil, which was unknown at the time of the Viking missions, could have interfered with the detection of organics by breaking them down during the analysis process. Advancements in technology have since led to the development of more sensitive instruments. For example, the Mars Science Laboratory's Curiosity rover is equipped with the Sample Analysis at Mars or SAM suite, which includes a more advanced GCMS capable of detecting a broader range of organic molecules at lower concentrations. This has allowed Curiosity to identify simple organics in Martian rocks and soil, providing evidence that organics are present on Mars, albeit in low concentrations. Future missions continue to prioritize instrument sensitivity, employing cutting-edge technologies to enhance detection capabilities. This includes the use of more sophisticated spectrometers, improved sample preparation techniques, and the integration of complementary analytical methods to cross-verify findings. The environmental impact of space missions, particularly those exploring other planets like Mars, is a critical consideration in the planning and execution of these missions. This impact encompasses both the potential contamination of extraterrestrial environments and the broader implications for Earth's environment. Planetary protection and contamination. One of the primary concerns is forward contamination, where Earth-originating microbes are inadvertently transported to other planets. This is particularly significant for missions searching for life, as contamination could compromise scientific results by introducing terrestrial life forms that might be mistaken for native organisms. The Viking missions were among the first to implement stringent sterilization protocols to minimize this risk, using dry heat microbial reduction to sterilize the spacecraft. Despite these efforts, the possibility of extremophiles surviving the journey remains a concern, highlighting the need for ongoing improvements in sterilization techniques. Impact on scientific integrity. Contamination not only affects the potential ecosystems of other planets, but also the integrity of scientific research. If Earth microbes were to establish themselves on Mars, it could lead to false positives in life detection experiments, complicating the search for indigenous Martian life. This underscores the importance of robust planetary protection measures to preserve the natural state of celestial bodies for future exploration. Environmental considerations on Earth. The environmental impact of launching and operating space missions also extends to Earth. The production and launch of spacecraft involves significant energy consumption and the use of hazardous materials, which can contribute to pollution and resource depletion. Space agencies are increasingly aware of these impacts and are working to develop more sustainable practices, such as using greener propellants and improving the efficiency of launch systems. Ethical and policy implications. The potential environmental impact of space exploration raises ethical and policy questions about humanity's responsibility to protect other worlds and the broader cosmos. International guidelines, such as those established by the Committee on Space Research, COSPAR, aim to balance the pursuit of scientific knowledge with the need to preserve extraterrestrial environments.